The last problem we will consider will indeed be a challenging one. It will just be a slight modification of one we've already done, namely a block on a ramp. Before, the ramp was fixed to the ground and did not move. Now we're going to let the ramp sit on a level, frictionless surface, and we will allow it to move. So as the block right here slides down the ramp itself will be moving in the opposite direction. So what we'll take is a block of mass m, a ramp of mass capital M, and have an angle theta. We'll take all surfaces to be frictionless, and what we'll want to find is the acceleration of the two objects and the normal forces between the block and the ramp and between the ramp and the surface. We're going to follow the same procedure we've done before by drawing a free body diagram, picking in a frame of reference, applying F equals ma, looking at things that constrain the motion of the objects, and eventually set up a set of n equations for n unknowns and then do the math. However, before we get into that procedure, we should consider briefly what is going on here. The block will in fact be constrained to move along the angle right here on the ramp. And the ramp, however, will be moving in the opposite direction. What that means is as the ramp moves or accelerates, the block will move down, but it will not move down at the angle theta relative to the ground. It will be moving at the angle theta, but only relative to the ramp, but the ramp will be accelerating, so it will not be an inertial frame of reference. Typically what we do in these kinds of problems is we take and we put our frame of reference, our axes, on the ramp and angle the x-axis down the ramp so that all we need to do is find the x component of the acceleration of the block. Here we can't do that because this frame of reference will not be an inertial frame of reference. We cannot use Newton's second law in a frame of reference attached to the ramp. Instead, we're going to need to take our frame of reference and attach it to the ground because that'll be our inertial frame of reference. The ramp will be moving relative to the ground and the block will also be moving relative to the ground. However, because the ramp isn't stationary, the block will not be moving down at an angle theta. It cannot. Consider the following extreme cases. Let's take the ramp being extremely light and the block relatively heavy. Then the ramp, being very light, will move out of the way very quickly, which means the block will basically fall straight down. It will not move down at an angle theta. It'll move more or less vertically straight down. In fact, in the limit where the ramp becomes essentially massless, the block will be moving straight down. Now consider the other extreme, where the ramp is very, very heavy and the block is very, very light. Well, now this really massive ramp will hardly move at all due to the pressure caused by the very, very light block. So this will stay more or less at rest. And then the block will more or less move down at the angle theta. As a result, the block will move down at some angle between theta and 90 degrees. I don't know what angle that'll be. Therefore, I don't know what angle to basically position the xy axes to simplify the math. And because we can't simplify the math, unfortunately we're stuck with complicated math. So the easiest and simplest way to do this is simply make our axes horizontal and vertical because of the way these two objects have to be moving. Okay, with that in mind, now we can start drawing the free body diagrams. First thing I want you to do is take a stab at it yourself. Just go through this list of forces and identify all the forces acting on the block and the ramp. Okay, first thing we can do is eliminate tension and friction. There are no ropes involved, and we've assumed all of our surfaces are frictionless. And as usual, we will consider air resistance to be negligible. The only two forces we have to worry about are the weights of the objects, and they're indicated right here, and the normal forces between the surfaces. The normal force between the ramp and the block will be up at this angle right here, which will be perpendicular to the surface of the ramp. And the normal force on the and the block onto the ramp will be equal and opposite. So those two will be action-reaction pairs. The ramp will push up on the block will push down on the ramp. In addition, we have the surface right here, the ground, pushing up on the ramp. And those are all the forces we have. Then, as I already mentioned, our frame of reference cannot be attached to the ramp because that's a non-inertial frame of reference. So this axis might look like it'll be good, but in fact it will not. So instead we'll put our XY axes in our frame of reference attached to the ground. That is the best we can do. And we'll have to deal with the fact we'll have to find the X and Y components of the acceleration of the block. So now what we can do is just write down F equals ma for both of the objects. Noting all accelerations, again, remember, will be measured relative to the ground. So, first thing we need to worry about is this vector right here, that's normal force, will have to be broken down to its X and Y components. Recall from our geometry we did with a block on a ramp, if this angle is theta, this angle right here will also be theta, which means this angle up here between the vertical and the normal force will also be theta. These are alternate interior angles, so these two angles will be equal. Okay, with that geometry in mind, we can now write down F equals ma for both of the objects. So write down F equals ma first just for the block right here. And do that in your notes. Okay, for the block, we just need to read the forces straight off from the free body diagram. The only horizontal force we have is one of the components of the normal force, which will be n times the sine of theta, because that'll be this force right here, n times the sine of theta. That equals the mass of the block times its acceleration in the x direction. Now here we'll also be accelerating in the y direction in response to gravity pushing down and a component of the normal force pushing up. So it'll be n sine theta minus the weight, mg, equals m times a sub y. And that'll be for the block. Now what I want you to do is do the exact same thing for the ramp. Okay, for the ramp, we will have, again, in the x direction, the only component will be this component of the normal force. This will also be theta right here. So n sine theta, but notice it's in the negative x direction, so it's minus n sine theta, equals the mass of the ramp times the acceleration of the ramp, and I'll simply call that capital A. Vertically, all of these vertical forces have to cancel out, so that'll be the normal force minus the weight of the ramp minus this component of the normal force. Pointing down, all of those have to add up to 0 because the ramp will in fact be forced to be accelerating only horizontally. So those forces must add up. Now notice, what we have here are 4 equations, but we have 5 unknowns. We have the 2 normal forces, we have the x and y components of the block's acceleration and the ramp's acceleration. That means we have an underdetermined system. We need one more way in which all of these unknowns are related. The way we're going to find our additional equation is to note that even of reference, the block is still forced to accelerate along that surface. Even though that's a non-inertial frame of reference, that constraint is still valid. So what we need to do is figure out how are we going to relate the constrained motion of the block with respect to a non-inertial frame of reference to its motion with respect to an inertial frame of reference. And the way we can do that is using the relative velocity equation that we've used before. Namely, the velocity of the block with respect to the ground must equal the velocity of the block with respect to the ramp plus the velocity of the ramp with respect to the ground. That is just our relative velocity equation. However, we don't want velocities, we want accelerations. So what we're going to do is take the derivative of this equation and we get a similar equation, but now for accelerations. Now, typically when we did relative velocity problems before, this right here, this last term would have been 0 because our 2 frames of reference were both moving at constant velocities, and therefore that had no acceleration. Now this is an acceleration. However, these terms, some of them we've already run across. This right here is the acceleration of the block with respect to the ground. That's what I've called little a. This right here is the acceleration of the ramp with respect to the ground. That's what I've already called capital A. And the acceleration of the block relative to the ramp. This right here is what is constrained to be along the angle theta. So we can take and combine all of these together. Oh, before we move on, note this cannot be used in Newton's second law. These are the two that can be moved in Newton's second law. As we're going to take and use the relative motion equation and simply substitute in our previous notation that little a must equal this acceleration plus capital A. But this is a vector equation. Because it's a vector equation, it has an x and a y component. So what that means is the x component of the acceleration here must equal this x component plus that x component. Well, this x component is just what I've called capital A. Here, the y components must also add up, but this y component is 0. This triangle shows me how the x and y components of the acceleration of the block relative to the ramp must be related. They have to match this triangle and be related by the angle theta, or the tangent of this angle must equal the opposite divided by the adjacent. So that's what I've written down right here. I put the minus sign in here because the angle theta is below the axis, so it's a negative angle. So the tangent of theta must equal the ratio of the acceleration of the block relative to the ramp in the y direction divided by that acceleration in the x direction. Then we can take these two equations and eliminate the two non-inertial accelerations in terms of the accelerations in the problem. So the tangent of theta must equal minus a sub y divided by a sub x minus capital A. Now we have our last equation. So with that done, we now have 5 equations and 5 unknowns. The unknowns are a sub x, a sub y, capital A, and capital N. The algebra to solve these 5 equations will in fact be incredibly messy. Probably don't want to do that through substitution or through typical algebraic manipulations. Instead, what we're going to use is either setting up a bunch of matrices or using the application that's already been written for TI calculators for solving polynomials and simultaneous equations, which essentially just solves the problem using matrices as well. And we'll plug in some numerical values. So what we're going to do first is rewrite all of these in the form, a standard form of coefficient times unknowns all added up on one side of the equation and all the constants on the other. So we're going to take these 5 equations. What I want you to do is rewrite them in the form of matrices, which is what you've done in the previous 2 videos. When you do that, this is what you get. This set of this matrix right here. What we're going to do is let the mass of the block be 1 kilogram, the mass of the ramp be 2 kilograms, and we'll let the angle be 30 degrees. That defines the problem. We can then plug numerical values into all of these, plug them into your TI calculator, and actually get a value for all the accelerations and the normal force. So what I want you to do is take a stab at doing that. What you should get for our answers are the acceleration of the block in the x direction is 3.77 meters per second squared. Its acceleration in the y direction is negative, which is what it should be, 3.27 meters per second squared. The ramp will be accelerating in the opposite direction at 1.89 meters per second squared. The normal force right here between the block and the ramp will be 7.54 newtons, and the normal force between the ramp and the ground will be 26.13 newtons. Now we need to ask ourselves, okay, do these make sense? Well, the acceleration of the block in the x direction should be positive or to the right, and we expect its acceleration to be less than the acceleration of the much heavier ramp, which is what it is. Capital A should be negative or to the left, which it is. A sub y should be negative or it's going down, which it is. So the accelerations make sense. Note that the normal force between the ramp and the block first must be less than the weight of the block, because the block has to fall down. But because the ramp's also accelerating out from underneath it, it should be less than what it would be if the ramp were held stationary. So namely, it should be less than its weight, 9.8, times the cosine of 30 degrees, which is what the normal force would be if the ramp were anchored and stationary. So it should be less than 8.49 newtons. And notice it is. So again, that makes sense. The normal force between the ramp and the surface should be less than the total weight sitting on it, because notice, essentially, the center of mass of this system must be moving down, because although the ramp isn't going anywhere, the block is moving down, and therefore its weight cannot be totally supported. So therefore N should be less than the total weight, which is what it is. The total weight is 29.4 newtons, and the normal force is only 26.1 newtons. Now, this angle right here should be something between 90 degrees and theta. It should be greater than theta and less than 90 degrees. So we can calculate the angle for the acceleration of the block, and we find it's about 41 degrees, which is in fact between 30 and 90, which again makes sense. So although we can't say our answer is definitely, unquestionably correct without actually doing an experiment, nonetheless, it does make sense. So we're done.